You've found Dreamtime Science, a peaceful corner where we unravel the mysteries of our universe one whisper at a time. Let the gentle current of discovery carry you towards sleep. You know what's fascinating? I've been thinking a lot about those everyday shapes around us, length, width and height, and then wondering, what if there's more to space than just those three? There's something remarkable about the idea that beyond what we can see and touch, there might be dimensions that stretch our imagination in quiet, surprising ways. I can't wait to share with you what that might mean, like stepping gently into a new kind of space that feels both strange and wonderfully familiar. If you find peace in these nocturnal discoveries, consider becoming a regular visitor to our quiet corner of science. Share in the comments what topic you'd love to dream about next. Let's prepare for tonight's journey. Find your most comfortable position, let tension float away from your body, and take 3 slow, peaceful breaths. The evening air is thick with the hush of anticipation, and somewhere, beyond the lattice of your ceiling and the reassuring geometry of your room, the universe stretches and folds itself in ways that defy the boundaries of our daily intuition. You lie back, tracing the familiar lines of your walls and windows, the sharp corners and flat planes, each a silent testament to the tyranny of the 3 dimensions we know so intimately. But tonight, as the world softens around you, we slip sideways, into the domain not just of physics, but of dreams, stories, and the wild-eyed imaginings of human culture. We drift gently toward the 4th wall, and beyond it, into the shimmering, strange territory where dimensions multiply and reality itself seems to dance. 3 dimensions are our native tongue, the language our bodies and senses speak without effort. Up and down, left and right, forward and back, this triad forms the invisible cage within which our lives unfold. But what happens when we peer past the bars or push our faces up to the glass? Popular culture has always found itself both enthralled and unsettled by this question, returning again and again to the tantalizing notion of a world beyond the one we can see and touch. The very phrase, the 4th dimension, hums with mystery, conjuring images of impossible spaces, realities just out of reach, and beings who move through them as lightly as we stroll down a city street. It is a question as old as curiosity itself. What lies beyond? Not merely in the sense of distant lands or the night sky, but in the heart of the very fabric of existence. The earliest echoes of this longing can be found in ancient myth, where gods and spirits flit through unseen realms, walking through walls, vanishing into thin air, or reaching into mortal affairs from invisible heights. Yet it was not until the blossoming of science and mathematics that the idea of extra dimensions began to take on a more precise, if still fantastical, shape. In the late 19th century, as the Victorian world pulsed with new discoveries and anxieties, a schoolmaster named Edwin A. Abbott penned a slim, satirical novel that would become one of the most beloved works of speculative fiction. Flatland, a romance of many dimensions. Abbott's tale is set in a 2-dimensional universe, a world as flat as a sheet of paper, where geometric shapes live, work, and dream. The protagonist, a humble square, narrates his adventures, revealing a society rigid with hierarchy and custom. Into this world comes the shocking visit of a sphere, a being from the 3rd dimension, who lifts the square out of flatland and grants him a momentary glimpse of a realm that transcends his imagination. Abbott's playful conceit is as sharp as it is profound. Through the eyes of the square, we are made to feel the terror and wonder of encountering a dimension beyond our own. What would it be like, he asks, to meet a creature who could appear and disappear, pass through walls, or see inside closed rooms, simply because they experienced a reality with an extra degree of freedom? For the Flatlanders, this is heresy, an affront to the natural order. For us, it is a lesson in humility, and a gentle prod to consider how limited our own perception might be. Abbott's legacy has rippled through the cultural consciousness, for more than a century, inspiring artists, writers and filmmakers to imagine worlds that curl and twist beyond the grasp of our senses. His Flatland, with its austere geometry and sly social commentary, became a template for exploring not just mathematical ideas, but the boundaries of human understanding itself. The very notion that we, like the Flatlanders, might be unable to perceive the true complexity of reality is at once unsettling and exhilarating. As the 20th century unfurled, the fourth dimension became a playground for all manner of cultural experimentation. In the art world, the Cubists, Picasso, Braque, and their cohort, sought to capture multiple perspectives simultaneously, fragmenting objects and faces as if attempting to render a four-dimensional truth on the two-dimensional canvas. The Russian abstract pioneer Kazimir Malevich spoke of the fourth dimension as an aesthetic goal, a kind of transcendence that painting alone could only hint at. The Surrealists, too, embraced the language of higher dimensions, using it to evoke dreamlike realities that flickered just beyond reach. Meanwhile, in the popular imagination, the fourth dimension took on a host of guises. Sometimes it was time itself, as in H.G. Wells's The Time Machine, where the hero's contraption slides not through space, but through the hidden corridors of temporal duration. Elsewhere, it was a literal spatial direction, invisible but ever-present, a shadow cast by objects and beings more complex than our own. In detective stories and pulp magazines, criminals vanished into the fourth dimension, and magicians claimed to reach into it for their tricks. The phrase acquired a patina of the occult and the uncanny, a catch-all for everything that could not be explained by common sense. Nowhere, perhaps, is the allure of extra dimensions more evident than in the fevered realms of modern science fiction and fantasy. Here, the fourth dimension is not just a mathematical abstraction or a metaphor for change. It becomes a stage on which the impossible is made possible, and where the rules of existence are rewritten with a flourish. Consider, for instance, the Tesseract, a word that has tiptoed from geometry textbooks into the language of cinema and comic books, carrying with it a freight of awe. In mathematics, a tesseract is a four-dimensional analogue of the cube, just as a cube is to a square. Its structure can be projected into three dimensions, casting strange, shifting shadows that seem to pulse and mutate as they are rotated. But in the hands of storytellers, the Tesseract becomes something more, a symbol of transcendence, a portal, a device that bends the known laws of space to its will. In Marvel's Avengers saga, the Tesseract is an object of immense power, a glowing cube that can open rifts between worlds, defy gravity, and bend reality itself. It is coveted and feared, a touchstone for the unknowable, and a reminder that the deepest mysteries are often couched in the language of dimensions. Elsewhere, writers like H.P. Lovecraft wove the fourth dimension into their tales of cosmic horror. In Lovecraft's universe, the boundaries between dimensions are thin and perilous, and beings from higher realities, shapeless, incomprehensible, slip through the cracks to haunt human dreams. In his story, The Dreams in the Witch House, the protagonist stumbles upon a geometry so bizarre that it allows movement outside the regular three dimensions. Here, the fourth dimension is not merely a source of wonder, but of existential dread, a reminder that the universe may be stranger and more indifferent than we could ever hope to know. These fictional depictions are not mere flights of fancy. They resonate so deeply because they tap into a very real sense of limitation and longing. Our minds, sculpted by evolution to navigate the three-dimensional world, struggle to conceive of what lies beyond. When we try, we reach instinctively for metaphor and story. We imagine beings who can step through walls as easily as we step over puddles, or who can see the insides of things without breaking their surfaces. This is the heart of the fourth wall in theatre and film, the invisible boundary between the audience and the stage, which, when broken, allows characters to address us directly, as if stepping out of their own reality and into ours. In recent years, the language of dimensions has crept into the world of entertainment in more literal ways. The term 4D is now emblazoned on movie theatres and amusement park rides, promising an experience that transcends the ordinary. In these venues, the fourth dimension is rendered as sensation, seats that shake and tilt, bursts of wind or sprays of water, scents wafting through the air. The goal is to collapse the distance between viewer and spectacle, to make you feel as if you are part of the action, tumbling through the story's world rather than watching from afar. Yet even as these attractions delight and startle, they are a kind of sleight of hand, a playful nod to the deeper questions that haunt our relationship with dimensions. For in truth, the fourth dimension, in its purest sense, remains forever just out of reach. We can project its shadows, build analogies, and simulate its effects, but to truly inhabit it would be to shed the constraints of our bodies and senses, to become something else entirely. Still, the urge persists. Across the vast tapestry of pop culture, dimensions beyond the third are invoked as metaphors for everything that eludes our grasp: the afterlife, alternate realities, the secret workings of fate. In the animated series Rick and Morty, portals yawn open onto universes with extra dimensions, each one a riot of impossible angles and surreal landscapes. In Christopher Nolan's film Interstellar, the protagonist finds himself in a Tesseract-like structure, able to perceive and interact with time as if it were a spatial direction. Here, the fourth dimension becomes a means of both salvation and revelation, a way of reimagining love, memory, and destiny. Such images are not confined to the screen or page. They seep into our language and dreams, shaping the ways we think about everything from parallel universes to the inner workings of consciousness. To speak of thinking outside the box is to invoke, unwittingly, the spectre of extra dimensions, the idea that solutions may exist beyond the plane of our current understanding. In philosophy and spirituality, the fourth dimension is sometimes invoked as a symbol of enlightenment, a space in which the apparent contradictions of ordinary life are resolved, and a higher harmony is glimpsed. Of course, alongside this poetic yearning, there is a quieter, more skeptical voice. Some dismiss the language of extra dimensions as mere fantasy, a convenient gimmick for storytellers and charlatans alike. They point out, not without reason, that the mathematical fourth dimension, as used in physics and geometry, is a rigorously defined concept, not a catch-all for the supernatural or the impossible. And yet, even the most hard-nosed rationalist must admit that the history of science is a chronicle of expanding horizons, the gradual realization that reality is deeper, stranger, and more interconnected than we had ever supposed. The cultural dance with dimensions is thus a kind of rehearsal for discovery, a way of preparing our minds for the possibility that the universe holds more than meets the eye. Through stories, art, and imagination, we sketch the outline of what might lie beyond, even as we remain anchored in the familiar. The fourth wall, in all its forms, becomes a membrane, permeable, fragile, and charged with possibility. It is the place where curiosity presses its palm against the glass, peering at the world as it might be, not just as it is. As you settle deeper into the folds of night, the echoes of these stories swirl around you. The square's bewilderment in flatland, the shimmer of the Tesseracts surface, the haunted geometry of Lovecraft's spaces, all these are invitations to wonder. They remind us that our sense of reality is as much a product of imagination as of perception, and that the dream of extra dimensions is, in the end, a dream of freedom. Yet, outside your window, the world remains steadfast in its threefold form. The moon carves its arc across the sky, the trees cast their shadows, and the night deepens. Somewhere in the darkness, a door stands ajar, a threshold waiting to be crossed, not by the body, but by the mind. And so we linger, poised at the edge of the known, listening for the whisper of something vast, strange, and beautifully unfinished. Let us drift now, gently, beyond the familiar shores of length, width, and height, those comforting dimensions that cradle the world as we know it. In this quiet moment, as the world hushes into the softness of night, allow your mind to loosen its grip on the tangible and reach, with measured curiosity, into the realm where geometry begins to shimmer with something almost magical. Here, the very notion of beyond takes on a new shape, a shadowed corridor branching away from the three-dimensional world, beckoning us to peer into the mysteries of higher dimensions. The ancients, wise in their own ways, mapped the world using lines, planes, and solids, 1, 2, and 3 dimensions. A point, without breadth or width, marks the 0 dimension, a mere location. A line, infinite in slenderness, stretches into the 1st dimension. A plane, broad but flat as the surface of a tranquil lake, forms the 2nd. And then, the 3rd dimension, space as we know it, swells out, granting volume, the proximity of things, the possibility of moving around and through. This is the world our senses are tuned to, the world of cubes, spheres and mountains, of clouds and rivers, trees and bones, all shaped and moulded by the interplay of 3 axes. But what then lies just beyond? If the leap from a flat square to a cube is as profound as stepping from a shadow into light, what happens when we attempt to take yet another step, to imagine the 4th dimension? It is here that the ground beneath our reason begins to tremble, and the edges of comprehension blur and shimmer. Mathematicians, with their unerring appetite for abstraction, named this hypothetical structure the hypercube, or more poetically, the Tesseract. It is a word that seems to hum with possibility, conjuring images of impossible geometry, of shapes folding through themselves in ways that defy the mind's eye. To reach for the Tesseract, we begin with a point, stretch it to a line. The line becomes a square, the square extrudes into a cube. Then, in an act of intellectual acrobatics, the cube itself is projected outward orthogonally into a direction that does not exist in our world, a 4th spatial axis. The tesseract is to the cube as the cube is to the square, a shadow of a higher reality cast down into our 3-dimensional space. It is almost impossible to truly see a tesseract, for our eyes and brains evolved to interpret only 3 dimensions. Yet through analogy and mathematics we can chart its outlines. Imagine for a moment the shadow of a cube upon a wall, a skewed hexagon, its lines and angles distorted by the intrusion of 3 dimensions into 2. In the same way, the shadow of a tesseract in our world appears as a strange nested cube within a cube, connected by lines that seem to cross through solid space. The tesseract, in its full glory, exists only in mathematical abstraction, a region of possibility where things could in theory be connected in ways that seem paradoxical to us. Faces become cubes, edges become squares, and the fabric of space itself appears to ripple with new freedoms. For centuries, such musings were the province of mathematicians, artists, and dreamers. But in the early years of the 20th century, a quiet revolution began to unfold, one that would forever change our understanding of the universe and our place within it. At the heart of this revolution was a man with a shock of wild hair and eyes that seemed to peer always just beyond the horizon, Albert Einstein. Before Einstein, time was an absolute universal river, flowing evenly for all, indifferent to the lives and motions of those who floated upon it. Space and time were separate, each with its own rules and rhythms. Yet, as Einstein pondered the results of experiments and the strange behavior of light, he began to suspect that this division was an illusion, a trick of perception rather than a reflection of deeper reality. In 1905, Einstein published a series of papers that would become known as the special theory of relativity. In them, he proposed that space and time are inextricably intertwined, woven together into a single four-dimensional fabric, space-time. In this new conception, time is not an unyielding backdrop against which events unfold, but a dimension much like length, width, and height, a direction in which things can move, though constrained by the peculiarities of causality and entropy. The speed of light, long considered a mere property of the universe, became the ultimate speed limit, the thread that stitches together the very structure of space-time. The implications of this union are both subtle and profound. If you move quickly through space, you move more slowly through time. If you stand still, your clock ticks at the fastest possible rate. Imagine two twins. One remains on Earth, the other journeys away at nearly the speed of light. When the traveler returns, she will have aged less than her sibling, a consequence not of magic, but of the geometry of space-time itself. Time and space bend and stretch in response to motion, no longer rigid, but supple and dynamic. Yet Einstein's vision did not stop there. Over the next decade, he sought to understand gravity not as a force, but as a manifestation of the curvature of space-time. In the presence of mass and energy, space-time bends, and objects follow the curves of this geometry. Planets circle stars, not because they are tugged by invisible threads, but because they move along the straightest possible paths in a curved four-dimensional continuum. Gravity, then, is geometry made manifest, a whisper of the fourth dimension, felt in every falling apple and orbiting moon. If time is a dimension, why do we experience it so differently from space? We may wander freely through the three spatial axes, but time moves ever forward, dragging us inexorably from past to future. Some physicists have likened this to the peculiar geometry of space-time. While all four dimensions are woven together, time has a unique signature, a distinction in the equations that marks it as different from the others. It is as if we are fish in a river, able to swim to and fro in the water's width and depth, but carried ever onward by the current of time. This idea, that time is both like and unlike the spatial dimensions, is echoed in the mathematics of relativity. In the famous equation for the interval between events, time enters with a negative sign, setting it apart from the positive contributions of length, width, and height. This subtle difference gives rise to causality, to the arrow of time, and to the impossibility of reversing the flow of events. The fourth dimension, though mathematically similar to the others, is marked by this fundamental asymmetry, a reminder that the universe, for all its elegance, is not perfectly symmetrical. As our understanding grew deeper, the notion of additional dimensions, beyond even the fourth, began to seep into the fabric of physics. In the 1920s, Theodore Kaluza and Oscar Klein proposed an audacious idea. What if gravity and electromagnetism could be united, not by new forces, but by the hidden geometry of a fifth dimension? In their model, the universe unfurls into an unseen direction, curled up so tightly that we cannot perceive it directly. This extra dimension, invisible to the naked eye, might explain the deep connections between the forces of nature. Decades later, as physicists sought to reconcile the jittery world of quantum mechanics with the smooth curves of general relativity, the idea of multiple dimensions re-emerged with renewed vigor. String theory, a framework both tantalizing and elusive, proposes that the fundamental ingredients of the universe are not point-like particles, but tiny vibrating strings, each resonating with its own frequency. For the mathematics to work, these strings require not 3, not 4, but 10 or even 11 dimensions, vast, unseen spaces folded and curled upon themselves at scales so small they defy imagination. In the world of string theory, the extra dimensions are compactified, rolled up into shapes known as Calabi-Yau manifolds. These are spaces of exquisite complexity, their surfaces twisted and knotted in ways that give rise to the properties of particles and forces we observe. The vibrational patterns of strings echoing through these hidden chambers determine whether a particle will become an electron or a photon, a quark or a neutrino. The universe, it seems, may be a symphony played not just in the open air of 3 dimensions, but in the hidden alcoves and corridors of a multidimensional hall. Yet for all its mathematical elegance, the idea of higher dimensions poses a formidable challenge to our intuition. Our minds are sculpted by eons of evolution to navigate a 3-dimensional world. We can draw analogies, create models, and manipulate symbols, but true visualization eludes us. To imagine a 4th spatial dimension is to attempt to see the back of one's own head without a mirror, a task both tempting and impossible. Artists and writers have long revelled in this paradox, weaving tales of worlds that cannot be seen but only hinted at. In Edwin Abbott's Flatland, for instance, the inhabitants of a 2-dimensional world are visited by a being from the 3rd dimension, a sphere, who appears to them first as a point, then as a growing circle, and finally as a shrinking dot before vanishing altogether. For the Flatlanders, the 3rd dimension is a source of terror and wonder, its effects visible but its reality forever just out of reach. In a similar way, we might imagine ourselves as the inhabitants of Spaceland, glimpsing only the shadows and projections of higher dimensions, unable to grasp their full reality. Even so, we find ways to reach for understanding. Mathematicians use projections, flattened images of higher dimensional shapes, to glimpse their structure. Computer simulations render tesseracts as morphing wireframes, faces folding through themselves in hypnotic dances. Physicists manipulate equations whose symbols encode the hidden symmetries of multidimensional spaces. Each approach is an attempt to bridge the gap between the world we know and the vaster reality that mathematics suggests. And yet the question lingers. Do these higher dimensions truly exist, or are they merely convenient fictions, scaffolding for our equations rather than bricks in the edifice of reality? We have no direct evidence for the existence of extra dimensions. They remain, for now, an elegant hypothesis, a tantalizing possibility hidden in the fabric of the cosmos. Experiments at the frontiers of physics, such as those conducted at the Large Hadron Collider, may one day reveal their presence, perhaps through the creation of miniature black holes or the subtle leakage of gravity into realms beyond our sight. Until then, the higher dimensions exist at the hazy boundary between mathematics and reality, a reminder of both the power and the limits of human imagination. As you nestle deeper into the quiet of night, let your mind wander through these corridors of thought. The universe, in all its strangeness, is not merely what we see, but also what we can imagine, what we can reach for in the darkness, guided by the faint glimmer of reason and wonder. Somewhere, perhaps, in the folded spaces beyond our perception, the secrets of reality await discovery, their shadows cast softly upon the walls of our dreams. And so, we find ourselves perched at the threshold of possibility, gazing into the interwoven tapestry of space and time, of dimensions both seen and unseen. The journey is far from over, for the universe is not yet done, revealing its hidden symmetries, its secret passageways. What, then, lies beyond the geometry of space-time? What strange and beautiful truths await us as we press onward, following the faint trail of curiosity into the deeper mysteries of the cosmos? In the silent hours between midnight and dawn, when the boundaries between waking thought and drifting slumber seem most porous, the mind finds itself open to strange vistas. It is here, in this liminal landscape, that we may dare to ask, if our world is but a thin slice through a richer, multidimensional loaf, what tools have we crafted to peer beyond our slice, to glimpse the shape of the whole? This is the tale, winding and luminous, of how scientists and philosophers have sought to reach through the veils of perception, how, with mathematics, clever experiments, and full of mind-bending models, they have tried to touch the fourth dimension, and perhaps even more. The urge to peer beyond our immediate senses is an ancient one. Early geometers, long before the word science was coined, puzzled over lines, planes, and solids, those fundamental forms that fill our three-dimensional existence. But it was not until the 19th century that the mathematical imagination began to truly strain against its own walls. The Scottish mathematician William Rowan Hamilton, lost in reverie as he walked the towpath of the Royal Canal, felt the spark of inspiration that would lead him to invent quaternions, a new algebraic system that for the first time described rotations not just in the plane or space, but in 4 dimensions. Though the physical meaning of these extra dimensions was unclear, the mathematics was sound, and for some intoxicating. In the drawing rooms and lecture halls of Victorian Europe, the concept of the fourth dimension became a subject of fascination and debate. Charles Howard Hinton, a Cambridge-educated philosopher and science writer, coined the very phrase fourth dimension and invented the word Tesseract to describe a 4-dimensional analogue of the cube. Hinton's writings, dense and visionary, invited his readers to imagine shadows of higher dimensional forms projected into our familiar 3-dimensional space. He even devised a set of colored wooden cubes, Hinton's cubes, to help students visualize the bewildering process of unfolding a tesseract, much as one might flatten a cardboard box. But mathematics alone could only take the imagination so far. To truly investigate the existence or influence of higher dimensions, scientists needed tools, experiments that could tease out the subtle fingerprints of dimensions beyond the reach of direct perception. Here, the 20th century brought with it an unexpected ally, the quantum world, where the rules of everyday logic are gently, or sometimes violently, overturned. Consider the famous double-slit experiment, a staple of quantum mechanics. It begins simply enough. Fire a stream of particles, say photons, at a screen with 2 narrow slits, and observe the pattern they make on a detector placed behind the screen. If the photons behaved like classical marbles, they would pass through one slit or the other, forming 2 neat piles. But what we see is something stranger, an interference pattern, a series of light and dark bands, as if each photon were a wave passing through both slits at once, interfering with itself. If we place detectors at the slits to determine which path each photon takes, the pattern collapses, and we return to the expected 2 piles. Somehow, the act of measurement changes the outcome. In the 1970s, physicist John Archibald Wheeler proposed a haunting twist on this setup, known as the delayed choice experiment. What if, he wondered, the decision to observe which path the photon took was made after the photon had already passed through the slits, but before it hit the detector? In other words, could a future choice affect the past behavior of a quantum particle? When the experiment was finally performed, the results were unmistakable. The pattern on the detector depended on whether a measurement was made, even if that decision came after the photon had chosen its path. In the quantum realm, the distinction between past and future, between cause and effect, becomes slippery. This revelation led to even more elaborate experiments, such as the delayed choice quantum eraser devised in the 1980s by Yoon-Ho Kim and colleagues. Here, entangled photons are used so that the act of measuring one photon can retroactively change the information available about its partner. The experimenters can, in a sense, erase the which path information after the fact, restoring the interference pattern as if the measurement had never occurred. The quantum eraser does not simply confound common sense. It hints at a reality where information, observation, and causality are woven together in ways that may transcend our 3-dimensional intuition. Some physicists, seeking to explain these quantum oddities, have speculated that higher dimensions may play a hidden role. In certain interpretations, the strange correlations observed in entangled particles, what Einstein famously called spooky action at a distance, might be the shadows of connections in a deeper, multidimensional space. While these ideas remain speculative, they illustrate how the search for tools to study higher dimensions is not limited to the abstract realm of mathematics, but spills over into the very heart of experimental physics. Yet mathematics remains a primary lantern in the darkness. The Tesseract, or hypercube, is perhaps the most celebrated icon of the fourth dimension. Like its humble cousin the cube, the Tesseract can be defined by its vertices, edges, faces, and so forth. In 3 dimensions, a cube is bounded by 6 square faces. In 4 dimensions, a tesseract is bounded by 8 cubic cells. To describe a tesseract mathematically, one simply writes down the set of points x, y, z, w, where each coordinate can be either 0 or 1. This produces 16 vertices, 32 edges, and so on. The numbers quickly outstrip the tidy symmetry of the cube. But how does one see a tesseract? We cannot, of course, perceive 4 spatial dimensions directly, but we can project the shape into lower dimensions, much as a 3-dimensional object casts a 2-dimensional shadow. The most famous such projection is the Schlegel diagram, which renders the tesseract as a cube within a cube, connected by lines that represent the 4th-dimensional edges. When rotated in computer simulations, the tesseract morphs and folds in ways that seem almost alive, its geometry mutating through the limited window of our 3-dimensional gaze. There are stranger objects still. The Klein bottle, for instance, is a surface with no inside or outside, a one-sided shape that cannot be constructed in 3 dimensions without self-intersection. Named for the German mathematician Felix Klein, it is the 4-dimensional cousin of the Mobius strip, which you may recall is a ribbon with a half-twist, forming a loop with only one surface. A true Klein bottle can only exist in 4-dimensional space, where it bends through the extra dimension to join its ends without crossing itself. In 3 dimensions, any attempt to build a Klein bottle results in a structure with a self-intersecting neck, a reminder of the limits imposed by our spatial prison. Such models serve not merely as mathematical curiosities, but as bridges for intuition. With the rise of computer graphics, researchers and artists have collaborated to create visualizations that hint at the grace and complexity of higher dimensional forms. Rotating tesseracts, unfolding polytopes, and animated Klein bottles dance across screens, inviting us to broaden the boundaries of imagination. These digital tools have rekindled an almost childlike sense of wonder for students and scholars alike, revealing that the language of higher dimensions, though subtle, is not beyond translation. Beyond the mathematical and visual, physicists have sought experimental fingerprints of higher dimensions in the fabric of reality itself. String theory, for example, proposes that the fundamental constituents of the universe are not zero-dimensional points, but tiny vibrating strings, whose patterns of vibration correspond to different particles. Crucially, the mathematics of string theory requires not 3, but up to 10 or 11 spatial dimensions to be consistent. The extra dimensions, so the theory goes, are compactified, curled up so tightly that they are invisible at human scales, like a garden hose viewed from afar appearing as a simple line, its circular cross-section hidden from view. To test such theories, physicists have turned to high-energy particle accelerators such as the Large Hadron Collider. Here, protons are smashed together at near light speeds in hopes that the resulting spray of particles might betray the influence of hidden dimensions. For example, if energy seems to inexplicably disappear from a collision, it might be leaking into dimensions beyond our perception. While no conclusive evidence has yet emerged, the search continues, as persistent as the tides. Elsewhere, cosmologists study the cosmic microwave background, the afterglow of the Big Bang, for subtle patterns that might hint at the shape of the universe's extra dimensions. Gravitational waves, those ripples in the fabric of space-time first detected in 2015, offer yet another window. If higher dimensions exist, they may alter the way these waves propagate, leaving telltale signatures in the data. The universe, it seems, is a kaleidoscope whose shifting colors and patterns may reveal clues about the hidden architectures that support it. Even in the realm of pure mathematics, the study of higher dimensions has yielded tools that ripple outward into unexpected domains. The concept of manifolds, spaces that locally resemble flat Euclidean geometry, but may curve and twist globally, has become central not only in theoretical physics, but in robotics, data science, and beyond. The n-dimensional sphere, or hypersphere, generalizes the familiar circle and globe to any number of dimensions, providing crucial insights into probability, information theory, and the geometry of the cosmos. Perhaps most evocative are the ways in which these mathematical abstractions force us to reconsider our place in the universe. In Flatland, A Romance of Many Dimensions, a novella written by Edwin Abbott Abbott in 1884, a two-dimensional square encounters a mysterious sphere which can only be perceived as a series of changing cross-sections. The square's struggles to comprehend the third dimension serve as a parable for our own limitations, and for the humbling possibility that even the grandest structures of our reality may be mere shadows of a deeper order. As our tools have grown more sophisticated, so too have our questions. The search for higher dimensions is not merely an academic exercise, but a journey that probes the very foundations of knowledge. The boundaries between mathematics and physics, between theory and experiment, grow porous. The delayed choice quantum eraser blurs the distinction between observer and observed. The Tesseract and Klein bottle, once the province of dreamers and eccentrics, have become touchstones for an age in which the impossible seems at times almost within reach. Yet for all our ingenuity, the fourth dimension remains elusive, a faint shimmer at the edge of comprehension. The instruments we wield, mathematical symbols, particle accelerators, computer simulations, are like lanterns in a vast, dark cavern, illuminating only the nearest walls. Each new experiment, each new model, serves both to clarify and to deepen the mystery. The more we learn, the more the boundaries of our ignorance expand, like the shadowy edge of a campfire in the wilderness. It is a humbling, exhilarating pursuit. To study higher dimensions is to acknowledge the limits of human perception and to celebrate the restless curiosity that drives us to transcend them. The kaleidoscope turns and the patterns shift. Quantum particles flicker between past and future. Tesseracts unfold and refold. Klein bottles slip through themselves in impossible contortions. Each tool, each experiment, is a gesture toward the infinite, a reminder that reality is not exhausted by what we see or measure. As the night deepens and the mind drifts toward sleep, one might wonder what new tools remain to be invented, what new experiments will reveal the hidden seams of the cosmos. In the silent spaces between dreams, the fourth dimension waits, subtle, patient, and filled with promise. The story, far from over, is just beginning to unfold its next layer, as hints of otherworldly order beckon us onward, deeper into the labyrinth of space, time, and possibility. In the hush of late night, with the gentle ticking of unseen clocks and the soft murmur of distant winds, let us drift together into the deepest waters of wonder, a place where science and philosophy entwine, and where the boundaries between what we know and what we can only imagine begin to blur. Here, beyond the veil of our familiar three-dimensional world, lies the vast, mysterious country of higher dimensions. And it is here, in this quiet moment, that we seek not only to understand, but to feel the significance of these realms for us, the fragile and searching creatures who look out from the surface of our planet and ask, what is our place, if the universe is wider and richer than our senses reveal? The notion of higher dimensions, those invisible directions that run perpendicular to every arrow we can point within our world, has long haunted the dreams of mathematicians, physicists, philosophers, and poets alike. For some, these extra dimensions are scaffolding for the deepest laws of nature, hiding the machinery that gives rise to the particles and forces we observe. For others, they are a metaphor, a way to gesture toward the infinite possibilities that lie just beyond the horizon of our perception. And yet, for all their abstraction, the idea of higher dimensions touches something at the core of the human spirit. It speaks to both our humility and our audacity, the humility to recognize the limits of our understanding, and the audacity to imagine what might lie beyond those limits. Consider for a moment how the revelation of an extra dimension would reshape the contours of our thought. When Edwin Abbott wrote his famous parable, Flatland, he invited us to imagine a world of two-dimensional beings, sentient lines and polygons, living their lives on an endless plane, blissfully unaware of the third dimension that floats above and below them. To the inhabitants of Flatland, the arrival of a sphere, a being from the third dimension, was at first incomprehensible, then terrifying, and finally transformative. The sphere could pass through their world in a series of bewildering cross-sections, appearing first as a point, then a growing circle, then shrinking again to a point, and vanishing altogether. For the Flatlanders, the visit of this strange being was a shattering revelation. It hinted at a reality far greater than anything their senses could grasp. Are we not, in some sense, the Flatlanders of our own universe? We move through three spatial dimensions, anchored firmly in one direction of time, convinced by habit and biology that this is all there is. And yet the mathematics of modern physics suggests that our reality may be only a slice of a much greater whole, a cross-section of a higher dimensional structure whose full extent we cannot see. If a creature from the fourth or fifth spatial dimension were to visit us, what would we perceive? Would it pass through our world as a fleeting apparition, its presence glimpsed only in fragments and shadows? Or might it change the very conditions of existence, like a hand passing through the surface of a pond, sending ripples of causality and possibility through the fabric of our lives? Such questions are not merely idle speculation. They press upon our most intimate sense of self, and upon the ancient riddle of free will. If, as Einstein's theory of relativity suggests, space-time is a four-dimensional block, every event, every moment, every decision already laid out in a vast, static tapestry, then are we truly free to choose, or are we but actors reciting lines written long before the curtain rose? The block universe, as physicists sometimes call it, is a universe in which past, present and future all coexist, equally real and unchanging. From the perspective of a higher dimensional observer, one who could see all of space-time at once, our lives would be like the grooves on a record, each moment fixed and immutable. This idea can be both unsettling and strangely comforting. Unsettling because it seems to deny the spontaneity and contingency that we cherish in our daily experience. Comforting because it suggests that every joy, every sorrow, every fleeting instant is preserved forever in the crystalline structure of the cosmos, never truly lost or erased. Yet even in the block universe, the question of free will is not so easily dismissed. For while the whole of space-time may exist, our consciousness moves through it one moment at a time, unfolding the story of our lives like a reader turning the pages of a novel. The future may be written, but we do not know its chapters until we arrive. In this sense, the experience of choice, the sense of freedom, remains real, even if its ultimate nature is mysterious. What if there are more dimensions than four? What if, as string theory proposes, there are 6 or 7 or even more spatial dimensions, curled up so tightly that we cannot perceive them directly? In such a universe, the landscape of possibility grows even richer. The intricate geometry of these hidden dimensions could shape the fundamental laws of physics, determining the masses of particles, the strengths of forces, even the very existence of life. Just as the shape of a violin's body gives rise to its unique voice, so the topology of higher dimensions could sing the universe into being, weaving together the harmonies of matter and energy. But can higher dimensions harbor life or consciousness? This is a question that beckons us into the territory of both science and speculation. Life as we know it is deeply dependent on the peculiarities of three-dimensional space, the way atoms bond, the structure of DNA, the very physics of chemistry and biology. In 4 spatial dimensions, for instance, the inverse square law of gravity would become an inverse cube law, and orbits would become unstable. Atoms would not hold together, and the familiar scaffolding of life would collapse. Yet this is only life as we know it. What forms might consciousness take in other dimensions, under different laws? Might there be modes of being so alien that we cannot even imagine them, intelligence etched into the folds of higher dimensional space, flickering in and out of our perception like lightning bugs on a summer night? These are questions, ends that stretch the imagination to its breaking point, and perhaps beyond. And yet, when we contemplate the possibility of higher dimensional consciousness, we are prompted to look inward as well as outward. For the human mind is itself a kind of multi-dimensional entity, not in the literal sense of extra spatial axes, but in the richness and complexity of its inner landscape. Our thoughts and feelings, memories and dreams weave together into patterns that are difficult to capture with the tools of linear description. The philosopher Henri Bergson once described consciousness as a continuous flux, a living multiplicity, more like a melody than a machine. Might our minds be attuned in some subtle way to dimensions beyond those of ordinary space and time? Might our moments of inspiration, déjà vu, or transcendence be glimpses, however fleeting, of a reality deeper than the one our senses reveal? Science, for all its rigor, is not immune to mystery. The very act of observing and measuring the universe changes what is observed, as quantum mechanics so elegantly demonstrates. The boundary between subject and object, between self and world, is blurred at the edges. In the quantum realm, particles can exist in superpositions, entangled across vast distances, their properties undefined until the moment of measurement. Some physicists have speculated that higher dimensions could offer new ways to understand these paradoxes, providing hidden channels for information or influence beyond our ordinary world. Others caution that such ideas are metaphors, not mechanisms, and that the true meaning of quantum strangeness remains elusive. Yet the dream persists that there is more to reality than meets the eye, and that by expanding our understanding we come a little closer to the heart of things. The search for higher dimensions is, in some sense, the search for meaning itself, the yearning to see the pattern behind the veil, to grasp the unity behind the diversity of phenomena. It is a quest that has driven thinkers from the ancient Pythagoreans, who saw the world in terms of number and harmony, to the architects of modern physics, who imagine the universe as a symphony of vibrating strings in a multidimensional arena. All of this, these abstractions, these speculations, these dreams, come to rest at last in the quiet intimacy of our own experience. When we gaze up at the night sky, we are looking not only across space, but also back in time. The light of the stars has travelled for eons to reach our eyes, bearing silent witness to the history of the cosmos. In those moments, we may feel both infinitely small and immeasurably connected, part of a web that stretches across dimensions we cannot see or name. The sense of awe that wells up in us is not merely an emotional reaction. It is, perhaps, an echo of our true nature, a reminder that we are woven from the same fabric as the universe itself. How, then, does our understanding of higher dimensions influence our perception of reality and our place within it? It is tempting to think that such knowledge would make us feel insignificant, mere specks in a vast and indifferent multiverse. But this is only one perspective. Another is that, by contemplating the possibility of higher dimensions, we become more aware of the strangeness and preciousness of our own existence. We recognize that the world we inhabit is not the only world possible, and that the laws and constants that give rise to life are delicately poised on the edge of chaos and order. Our consciousness, our ability to ask questions and seek understanding, becomes not an accident, but a profound mystery in itself. In this light, the search for higher dimensions is not only a scientific enterprise, but a spiritual one. It invites us to cultivate humility, to acknowledge the limits of our knowledge, and to remain open to the possibility that reality is stranger and more beautiful than we can yet imagine. It asks us to listen with all our senses and all our intuition for the faint music that may be playing just beyond the range of our hearing. And so, as you lie in darkness, letting the world fade to a hush, consider the possibility that you are more than the sum of your atoms, more than a fleeting pattern in the dust of stars. Perhaps you are a cross-section, a shadow of a higher dimensional self, moving through time and space, gathering experiences like pearls on a string. Perhaps your consciousness reaches out, in ways you cannot measure, into realms beyond the visible, touching mysteries that words and equations can only hint at. This is not a conclusion, but an invitation to wonder, to question, to dream. The veil of our world is thin, and beyond it lies a country vast and unexplored, waiting for the curious and the bold. In the gentle silence of the night, let your mind wander freely, unbound by the ordinary dimensions, and listen for the whispers of infinity. The journey is far from over, and the story is still unfolding. As our journey through the shimmering veils of dimensions beyond length, width and height gently drifts to a close, may your mind float like a comet tail fading into the hush of space. Let these quiet wonders lull you into peaceful contemplation, and when your heart seeks more dreamtime tales, return to wander once again among the cosmos of mystery.